We're working towards building up interesting probability models, and we just have one more little piece to cover. There's a collection of standard random variables that you need to know about. Here's a list of them. This list isn't here for you to go away and memorize it. It's a list that you should come back to whenever you're trying to build a new probability model for whatever data you have. And you think to yourself, is there some standard random variable that I could use here, or do I have to go to the bother of inventing my own? By the end of the course, you'll have seen all of these types of random variables used, and more importantly, you'll have learned what are the styles of problem for which different types of random variables are good at modelling. If you need to check up the details of any of these, using Wikipedia is perfectly fine. But watch out, because for some of them, Wikipedia uses one way to parameterize the random variable and NumPy uses another, and so it's easy for bugs to slip in. So whenever you use one of these random variables, make sure you read the documentation, make sure you read the probability density function carefully so you know exactly what you're working with. One small thing it's worth mentioning here: a discrete random variable returns integers, or more generally it could be a value from some finite or countable set, for example a coin toss or a card chosen at random. And a continuous random variable returns floating point numbers and has to have a smooth distribution function. There's a specialist term for this. If a random variable x returns values belonging to some set S, we say x is S-valued. A few other ways of saying it, we might say x has support S. Next, there's one variable that deserves special mention, the Gaussian random variable, also called the normal. We use this one all the time in machine learning and in probabilistic modelling more widely. It's easy to work with, and it's often a surprisingly good approximation when we can't be bothered to work with a true distribution. There's one very useful fact about them. If you take a normal and you add a constant and you scale it, you end up with another normal, just with different parameters. A plus b times normal of 1 is a plus normal of 0b squared, which is normal of a comma b squared. This sort of thing just doesn't work for most other random variables. If you took a binomial and added a constant, you wouldn't end up with a binomial. But it does work for a normal, and that's why normals are so easy to work with, and we'll be using this precise property time and time again in the examples we'll be working through. Okay, so now we know all the building blocks we need to start building rich probability models. The next video will get onto how we analyze them.